In this video, we will define the greatest common divisor of two polynomials, and we will see various properties of greatest common divisors of polynomials, which are completely analogous to the properties that we already know for greatest common divisors of integers. So let's start with a definition. Suppose we have two real polynomials f of x and g of x, such that not both of them are 0. Then a greatest common divisor of these polynomials is a real polynomial d of x, which satisfies the following conditions. Firstly, d of x divides both f of x and g of x. And secondly, if h of x is any other real polynomial which divides both f of x and g of x, then h of x divides d of x. For example, x plus 1 is the greatest common divisor of x squared plus 3x plus 2 and x squared minus 1. Now it is easy to check the first property, because we can write x squared plus 3x plus 2 as x plus 1 times x plus 2, and we can write x squared minus 1 as x plus 1 times x minus 1. The second property is more difficult to check, and we are not going to do it now. It will be much easier to check it once we develop the appropriate theory. But here we point out that unlike the case of integers, greatest common divisors of polynomials are not unique. For example, 2 times x plus 1 is another greatest common divisor of these polynomials, because again we can write x squared plus 3x plus 2 as now 2 times x plus 1 times x plus 2 over 2, which is a real polynomial, and similarly for x squared minus 1. But we do want to maintain uniqueness of the greatest common divisor. So the solution here is to add a new condition to the above definition, which will make the greatest common divisor unique. So before we add this new condition, we need some new definitions. So we say that a non-zero polynomial is monic if its leading coefficient is equal to 1. So for example, x cubed plus 3x squared minus 1 is monic, because the leading coefficient is the coefficient of x cubed, which is 1. But 2x squared plus 1 is not monic, because the leading coefficient is the coefficient of 2x squared, which is 2 and is not equal to 1. But of course, if we have any non-zero real polynomial f of x, which has leading coefficient a, then we can write f of x equal to a times g of x, where g of x is a monic polynomial. For example, with the polynomial f of x equals to x squared plus 1, which we have seen it is not monic, we can write it as 2 times g of x, where g of x, which is equal to x squared plus 1 over 2, is a monic polynomial. Okay, so now we are ready to give the definition of greatest common divisor. So it's exactly the same as what we said before, but we have one more condition. And the extra condition we have is that the greatest common divisor must be a monic polynomial. And with this extra condition, the greatest common divisor becomes unique. And from now on, we will be using this definition of the greatest common divisor and not the first one. Our task now is to show that greatest common divisors of polynomials exist and are unique. This is the content of the following theorem. Suppose we have two real polynomials f of x and g of x, not both equal to 0. Then their greatest common divisor d of x exists and it is unique. And furthermore, we can write it as a linear combination of f of x and g of x, meaning that we can find real polynomials r of x and s of x, such that d of x is equal to r of x times f of x plus s of x times g of x. And of course, as is the case of integers, we denote the greatest common divisor by GCD of f of x comma g of x. So let's proceed with the proof, and we start by showing uniqueness first. So suppose we have two real polynomials d of x and d prime of x, which both satisfy the conditions, meaning that they are both monic, they both divide both f of x and g of x, and if some other real polynomial divides both f of x and g of x, then it divides d of x and d prime of x. But these conditions mean that d prime of x must divide d of x, because we know that if something divides both f of x and g of x, so this something is d prime of x, then it must divide d of x as well. And vice versa, because d of x divides both f of x and g of x, then it must divide d prime of x. But now we know from the theory of polynomials we developed so far that d of x is equal to some constant c times d prime of x, or some real number c. But we also have the condition that d of x and d prime of x are monic, so c must be equal to 1, and so d of x must indeed be equal to d prime of x. So now we proceed to show that both the greatest common divisor exists, and it can be written as a linear combination of f of x and g of x. So to show this, we consider the set D of all monic polynomials, which are linear combination of f of x and d of x. That means that D is the set of all real polynomials k of x, such that k of x is monic, and we can find real polynomials a of x and b of x, such that we can write k of x as a of x times f of x plus b of x times g of x. So this set D is definitely non-empty. For example, if f of x is non-zero, we know that 1 of f and g are non-zero, and it has leading coefficient c, then definitely 1 over c times f of x belongs to D. Why? Because 1 over c f of x is monic, and in this definition here, we can take a of x to be 1 over c, and we can take b of x to be the zero polynomial. So definitely D is non-empty. So we look at all polynomials belonging to D, and we take one of them which has the smallest degree. Maybe there are several of those, we just take one. So let's denote it by d of x, and let's suppose that is equal to a of x times f of x plus b of x times g of x. What we are going to show is that this d of x is equal to the greatest common divisor of f of x and g of x. So definitely d of x is monic, and definitely if h of x divides f of x and h of x divides g of x, then h of x divides this linear combination. So h of x divides d of x. So the only thing that remains to show is that d of x divides f of x and d of x divides g of x. And since d of x is non-zero, by the division algorithm, we can find polynomials q of x and r of x, with the degree of r of x being less than the degree of d of x, such that we can write f of x as q of x times d of x plus r of x. Our aim here is to show that r of x is 0. And it will be enough to show this, because if we show that r of x is 0, then we will have f of x equal to q of x times d of x, and so d of x indeed divides f of x, and then an analogous argument shows that d of x divides g of x. So our task is to show that r of x is a zero polynomial. So suppose r of x is non-zero, and let a be its leading coefficient, and so we can write r of x being equal to a times f of x times s of x, or some monic polynomial s of x, and it's important here that the degree of s of x is equal to the degree of r of x. So I claim now that it is enough to show that r of x is a linear combination of f and g. Why? Because if I show this, then s of x, which is equal to 1 over a r of x, is also a linear combination of f and g. But s of x is monic as well, so s of x is an element of D. But this contradicts the minimality of the degree of d of x, because the degree of s of x is equal to the degree of r of x, which is smaller from the degree of d of x. So the only thing that remains to show is that this polynomial r of x is a linear combination of f and g. And we can show this because we know that r of x is equal to f of x minus q of x times d of x, and d of x is a linear combination of f and g. So let's do it. So we write r of x as f of x minus q of x d of x, and now we use that d of x is a of x times f of x plus b of x times g of x to get this line, and now we rearrange to get that r of x is 1 minus q of x times f of x times f of x minus q of x, b of x times g of x. So r of x is indeed a linear combination of f and g, and the proof is complete.